The alternative: finding a different energy source for most of society's energy needs. Once all the oil, coal, and gas runs out, you've likely heard of OP, like wind, geothermal, or tidal power, but do these approaches dream big enough? Could the answer to the energy crisis actually be something that sci-fi writers have been talking about for over 60 years? Although it's a long way off. Could humanity actually build a Dyson sphere one day? And just how far off are we from being able to do this? I'm Alex Molan, and you're watching Astrom. Join me today, as we examine the case for Dyson spheres and discover how the maths behind these gargantuan structures might make them not just possible, but actually plausible for our future energy supply. I was recently going through an online course when I came across the topic of Dyson spars, and they really caught my imagination. Dyson spars are crazy. They were first explored in a paper by British-American theoretical physicist and mathematician Freeman Dyson, who was considering the way hypothetical alien civilizations might try to power their society, and how we might spot them all. Life requires energy to live, and the more advanced a society, the more energy it seems to end up needing. Dyson thought that if an alien race was spacefaring, they might build a habitat in space near their local star to take advantage of its solar radiation. Over time, more and more habitats would be built until one day, most or all of the star would end up surrounded by a truly mammoth shell of habitats, which would capture and utilize all the radiation the star was emitting. This shell was eventually considered one single structure and came to be known as a Dyson sphere. Creating one would give a species access to a ridiculous amount of energy, sending their civilization into the next stage up in galactic exploration and expansion. Dyson got the idea after reading a science fiction book known as Star Maker, something he publicly credited. And indeed, this idea does sound a little like something out of sci-fi. It would be very hard and potentially take a very long time to build anything so large, and seems to be well beyond the capabilities of our own current civilization. That said, this sci-fi idea might need to be something we consider a little more closely. As the course I was learning from pointed out, there are just over 8 billion humans on Earth right now, and we collectively use 20 joules or 400 quintillion joules of energy per year. This sounds like a lot, and it is, particularly when you consider that the current estimated amount of remaining energy available in oil reserves is 6 to 10 as 22 joules or 66 tillion joules. Doing a little division, it becomes clear that we only have 150 years of oil reserves left if we continue burning it at our current pace. 150 years is really not that many, and given how quickly we are ramping up energy consumption globally, it's fair to assume that we might run out of oil sooner, even if more oil reserves can be found. I talk a little more about this subject in another of my videos here, which is why finding another mass source of energy, such as utilizing the energy available in sunlight, actually is quite appealing compared to what we gain from fossil fuels. The sun produces a staggering amount of energy, even if you're only considering the amount of light that hits our planet's surface directly. Let's use a little equation to show you what I mean. At this distance, the energy we receive from the sun is around 1,360 joules per second. Multiply this across approximately 1.11014 SIM of the sun's circular area as it cuts through space. Then multiply this again across the course of a whole year, all 36,000 seconds of it, and we would receive around 4.710 is 24 joule of energy. That's 10,000 times the energy we are currently using from oil, more than enough to cover our needs, assuming we could harness it. Obviously, capturing all that sunlight is a bit tricky to do in practice. And obviously, if we were to capture all of it, that would make life a bit difficult for any plants on the planet wanting to use that light for photosynthesizing purposes. But even if we got to the point where we were only using half of all that available energy, we would completely remove our need for fossil fuels and could have the energy necessary to support a significantly larger population. At the same time, forget 8 billion. We could sustain 40 trillion people here on Earth, at which point the biggest problem wouldn't be how to give all those people the energy you'd need to sustain their lifestyles, but where to put them. Increasing the population density by 5,000 times would go from there, being on average 7 people per square kilom, to being 35,000 people per square kilom, or 1 person per 3 square cm, so making this work might be a bit of a challenge without some creative housing plans. Regardless, this does seem like a good solution to the energy crisis. The jewels are there. So if we can already cover our population's needs by fully accessing only a small fraction of the sun's total output, the part hitting the Earth, we probably don't need to harness any more of it just yet. However, looking to the future, that won't always be the case. Reaching 40 trillion people is actually not that far off, at least on the scale of human history. Our population is currently growing at a rate of 0.88% a year. At times, this number has been as high as 2%. For simplicity, let's just take a nice round 1% figure and calculate using that. If we increase for the population size by 1%, every year, the cumulative growth